Hey guys, Greaves here. Hope everyone is well, keeping their social distancing and all that stuff. Okay, so let's continue with physics. I know everyone's excited. Okay, so we're going to take a look at something called a standing wave today. All right, so I put some instructions on the Google Classroom. I wanted you to watch the video first, right? So hopefully you saw the video. Obviously, I have tons of demos that we would do this in class. So it's been actually kind of good day to do this together. But it is what it is. We're doing the best that we can. Okay, so standing wave, right? So if you didn't, please go see the video, right? And if you did, so let's go. Well, what really happens in a standing wave? And it's kind of weird, right? So it's difficult to look at. But that guy actually did a pretty good job, I think, with those slow motion videos. But let's recap why this happens. Okay, so I have two waves, right? Here's A, here's B. They're going this way. But what happens when they meet? Well, right, I could get a big wave called C, right? Because waves, unlike you and me, are made of just energy, right? Only energy, right? What does that mean? Well, I can have two waves, right, occupy the same point in space at the same time, right? So if that's the case, right, these two waves, say that's a 1 and that's a 1, right, that could make 2. This happens because these waves are actually in phase, right? So in this particular case, we get constructive interference, right? Constructive interference. Now I'm going to be a little lazy today, okay? Now, that's one way waves can react, right? What about something that looks like this, right? So give that a 1 and give that a 1. This guy's going this way. This guy's going this way. Well, what's going to happen here? Well, at this point, I'm going to draw dotted lines, right? If this was A and this was B, this is what A would look like if it was here by itself. This is what B would look like if it was here by itself. But that's not the case in this particular case. Why is that? Because these two waves are out of phase. Right? And since I can have energy occupy the same point in space at the same time, we get some weird things. Like over here, I get big waves. Here, I get a small wave, and we call this destructive interference. Okay? All right, so this phenomenon, or this characteristic of a wave, is how we can get something called a standing wave. And it's called a standing wave because if you noticed on the video, it just looks like it's standing there in space, right? Anyway, let's take a look. All right, so suppose I have, now, by the way, you gotta, this is just physics, right? And explaining things, a lot of times this is very ideal. So let's suppose I send a wave, right, down a string, right? There's a wave that's gonna go down a string. This is a fixed end. I'm gonna fix that on another end, right? So this wave, traveling this way, right? It's going to hit this wall, right? Fixed end, fixed end. Well, what's going to happen? Well, we know what this wave hits a wall. We know 3 things always happen. We get reflection, transmission, and absorption. And yes, in fact, some of the wave energy will go through, but we're going to just consider the what? Reflected wave. And what happens when a boundary, right, a wave hits a boundary? It gets reflected, but it gets inverted. So I'm going to draw that in black, right? So coming back, right, in the opposite direction is the reflected wave. And there it is, looks like that. Okay? So now, what happens is the energy goes this way, bounces back, back and forth forever and ever and ever. Right? But what's happening here? Now look up here and over here. I get some spots where the waves, right, are now meeting, right? And they are going to be either in phase or out of phase. Well, look, I would say right here, what do we get? I'm just drawing, if that's a point on the wave, it's going to wiggle up and down, up and down, up and down. Same thing right here. It's going to wiggle up and down right here. Well, these are special points. These are points where the points on the waves are in phase. And what happens when waves are in phase, they're in phase, we get constructive interference. So we call these, believe it or not, so this point here, and this point here, we call an antinode, right? Why is it an antinode? Because, well, I should say, we call it an antinode, right? And what happens is we get constructive interference, right? Constructive interference will happen at an antinode, right? All right, well, how many antinodes do I have here? Well, in this particular case, I have 2, right? So what about here, here, and here? Well, these 3 points, let's do it like this. There's a red dot. That is called a node. Probably should have kind of started with this one first, right? Because here I have a node and antinode, but too late now, right? So a node, well, what do I notice from your video? We noticed that at those spots, there was no motion, or relatively no motion whatsoever at all. So what must have been happening? Well, at a node, right, we must have had what? Destructive interference, right? So these are special points, right, on something which we call on a standing wave. We get nodes where we get maximum destructive interference, 1, 2, 3, and I got antinodes where I have maximum constructive interference, right? Another question is, on this standing wave, how many wavelengths are here? Well, look, here's my, right? Remember the distance for the wave to complete one cycle. So guess what? In this particular case, so for this particular case, I have 1 wavelength, right? All right, so let's take a look. How many? So some questions on this kind of wave right here. How many antinodes? Well, let's go how many nodes? Nodes. How many? Well, 1, 2, 3. How many antinodes? 1, 2. How many wavelengths? 1. Okay, so there's a little bit of a pattern here. Let's see if I can tell. There are 3 nodes, right? And 1 less antinode, right? All right, so let's take a look at another standing wave. Okay, so let's do it like this. I'm going to send now. It's going to be a little weird. I'm sending only, right, this part of the wave down, and I'm going to get this part reflected back. So this guy goes this way, reflected back, boom, boom, boom. So let's ask a question. How many nodes? How many antinodes? How many wavelengths, right? So how many nodes do we have? Well, a node is where I have minimum, right? The smallest amount of movement. 1, 2. So there's 2 nodes. Let's see before. 3 nodes, 2 antinodes, 1 less. How many antinodes? Well, there's the part that's wiggling up and down, 1. And how many wavelengths do I have? Well, this is not a full wavelength, so I have to continue. This looks like I have a half a wavelength. Okay, well, let's take a look at this guy. Are there any other ones I can make? Well, let's see. Right. So there's a wave. Let's make the blue the reflected wave. There's the blue, reflected wave. Right. I don't know how well that looks, right? It's probably not too good, but you get the picture, right? Black is the original wave, blue is the reflected. So here's what I want you to do. Nodes, how many? Anti-nodes, how many? Wavelengths, how many? So I want you guys to do that. Take a minute, press pause, do whatever you want, right? So how many nodes? Well, let's do that in red. 1, 2, 3, 4. How many antinodes? 1, 2, 3, 3. How many wavelengths? There's 1 wavelength, right? Well, what do I have here? So it looks like I have half a wavelength, right? So what do I have? 1 and 1/2 wavelengths. Okay? And you should see that there's a pattern here. So this is called a standing wave. It's a special type of wave and something that we like to consider in any respectable intro physics class would definitely cover something like this. Okay, guys, so quick one for today. I'll send you some stuff, obviously, in Test Wizard, and enjoy your rest of your day. Okay, stay safe.